Alright, in this video we're going to be shooting and landing on the exact same plane. We start here, we end here on the exact same plane. So this is going to be a simplified derivation. It's a little bit easier than the next one that we're going to do. If we're going to be launching at a velocity of v at an angle of theta, which is in red there. And this velocity in v can be then resolved into two vectors, a horizontal vx vector and a vertical vy vector. And if you look at that triangle, then you can see that Vx I really messed that up, didn't I? Let's see here. Let's try that again. Vx would equal v times the cosine of theta, and Vy will equal v times the sine of theta. So those are our projectile motion components of the velocity that we're going to be using. We also know that the range equation, the horizontal distance that it travels, this would be the range all the way from here all the way over to where it lands. The range is going to be the horizontal velocity, Vx, times the time of flight. The vertical displacement, which we use as s, we use r for the horizontal displacement and s for the vertical displacement. S is going to be Vy times t plus 1/2 acceleration, which is going to be g t squared. So what we're going to do is we're going to actually solve both of these equations for time and then set them to be equal to get our equation for the range. So the first equation, the range equation, if we're solving that for time, is going to be time equals range over Vx, which is going to be v cosine of theta. That's doing this equation. Now to do this equation, there's a couple things we can do here. In for s, we put the vertical displacement. Well, we're starting here and we're ending here. So the vertical displacement is 0, which makes that really nice to do here. We can say 0 equals, and then what we can also do is divide the entire equation by t. And we're also going to put in our Vy. So we're going to have Vy as v sine of theta. But we're going to divide the whole equation by t, so that's going to get rid of one of this t, and it's all going to get rid of another one of these t. So I'm going to have plus 1/2 gt. Now if I solve this for t, then I'm going to have t equals, and I'm going to take the v sine of theta over to the other side, which will be a minus, and I'm going to multiply both sides by 2, so I'm going to have a minus 2v sine of theta all over g. So now I have a t for the horizontal and a t for the vertical, and of course those t's have to be the exact same time that it takes to get to this endpoint. So I'm going to set those to be equal. So I'm going to have range over v cosine of theta equals a minus 2 v sine of theta over g. I'm going to set those to be equal to each other. And I want to solve for range. So if I solve for range, I can just multiply this v cosine theta up on the top, and I'm going to have range equals a, I'm going to have a v times a v, I'm going to have a v squared in there. I'm going to have a minus, and I'm going to have a v squared, and then I'm going to have a 2 sine of theta cosine of theta all over g. And I could leave that equation like that. That could be my range equation, but we like to simplify things with trig identities if we can. And the trig identity we can use here is a double angle theory identity. Sine of twice the angle equals 2 times the sine of the angle cosine of the angle. So you see this part right up in here. So we're going to replace that with sine of 2 theta. So my equation is range equals a minus v squared sine of 2 theta all over g. And that is the derived equation for the range of a projectile shooting and landing on the exact same plane. So there's a couple interesting things about this equation. If you remember a sine curve, the maximum on a sine curve is at 90 degrees. This is 90 right here. 90 degrees. So this sine of 2 theta will be a maximum. It'll be a 1 if the theta is 45, because 45 times 2 is 90, and sine of 90 would be 1. So this thing is going to max out. It's going to get the farthest range. Whatever the velocity or the gravity is, it's going to give me the farthest range if the angle is 45 degrees. 45 degrees is the maximum angle to get the maximum distance. Now, after below and above 45 degrees, there's always going to be two angles that give you the exact same range. And those angles are going to actually be complementary, which means they add up to 90. So if I kind of ran out of room here, but if I shoot at like 30 degrees, like that, and I land, I could also then shoot it at 60 degrees, and it'll actually come to the exact same point. 30 and 60 will come to the exact same point. If I shot at 40 degrees and I shot at 50 degrees, whoops, I didn't do that right. I need to, let's see if we can go to another page here. Let's try to draw this out a little bit better. If I shoot at 30 and 60, okay, those will come to the same. And this one is all the way at 60. If I shoot at 20, and no, let's shoot at like 40 and 50. If I shoot at 40 and 50, 40 is going to go like this, and it's going to come out, and it's going to actually go a little farther. If I shoot at 50, it's going to come up here like this, and it's going to come to the exact same range. This is going to be 40 and 50, but they're going farther. If I shoot at 45, then come up here like this, I'm going to get my maximum range. 45 degrees gives you the maximum, because if you remember, it's range equals negative v squared sine of 2 theta over g. So 45 times 2 is 90. Sine of 90 is 1. That gives me my maximum possible distance. At 45 degrees, the range is always going to be a minus v squared over g. Don't worry about this minus, because what are you going to put in for gravity? You're going to put in a minus 9.81 here on the Earth, and so therefore it's going to be a positive value for your range, so you don't have to worry about that. So 45 degrees is going to be my maximum, and any complementary angles like 30 or like 40 and 50, or 30 and 60, or if I shot in here at 20 degrees and I shot up here at 70 degrees, it'd go way up here like this, then those would come out to be the same place too. So the higher the angle, the higher it's going to go, but not as far over as it's going to go. So complementary angles on the range equation.